Hi, we're going to take some notes on 6.4, 6.5, and a little bit of 6.6, but we're not going to do the examples because we'll be doing those in class. So let's talk about the fundamental theorem of calculus. Fundamental theorem of calculus is a big one, and so let's see if we can kind of break it down into its small pieces. I'm going to start by drawing a picture of a function that is defined by t, meaning the independent variable is not x, it's t. It really is the same thing as any other function. We're just saying it's a function of some variable t. And this function is continuous on an interval from a to b. Now, what if I want to look at a different function that is in terms of x, and x we are going to say is in the interval from a to b. Oops, I do want to include b here. So let's say x is right here. It could be any value between a and b. And I am going to define this new function, capital F of x, to be the integral from a to x of f of t dt. So I know an integral gives me the area under a curve. So we're looking from a to x. This area right here, from a to x, the area under the curve, is our function f, capital F of x. This is a function of x, which means it's dependent on x, right? If I moved, and I'm not gonna, I guess I can't do this completely, but if I moved this over a little bit, then capital F of x would be slightly smaller. You get what I'm saying, hopefully, that this capital F of x depends on where x is a function of x. Now, the fundamental theorem of calculus goes a little further to say, hey, if we take the derivative of this function, capital F of x, so the derivative of f of x, and if I do something to the left side of an equation, I have to do something to the right side. So the derivative of the integral from a to x of f of t dt, I am just left with lowercase f of x, where basically we're putting this value, in for t here. And this might not seem like a big deal, but this is, and it gives us our antiderivatives. So let's add this into the first part of our fundamental theorem of calculus. The first part says, if some function capital F of x is equal to the integral from a to x of f of t dt, then, then the derivative f prime of x is equal to lowercase f of x. The integral we know is the area under the curve. It's also a mathematical operation. It's basically summing up a rate of change. So this is the first part of our fundamental theorem of calculus, and I'm going to make this picture down here a little smaller. Now let's talk about the second part of the fundamental theorem of calculus. And we're still going to use this kind of same example. I'm just going to make it a little bit more detailed here. So let's say we're still looking at that function f of t. And I'm going to define capital F of x to be a function of this function from, let's say, c to x, which, let's go back then and draw in. We'll say c is right here. We'll go d, because I want to use a and b in this one, so I'm using different variables. And x, okay, x is a value between c and d. So capital F of x, we know, is this area under the curve. Well, what if I was looking to find, let's say, f of b minus f of a? And I'm going to add a and b into my x-axis here, where I'm going to put b right here, let's say, and a right here. Well, let's begin with f of b. F of b, I'm plugging in b for the x up here, is the integral from c to b of this function, f of t dt, f of t dt, and that is the area under the curve from c to b. All right, and let's go with a different color. Let's go with yellow. That might not be good. Let's go with that one. Okay. F of a, we're plugging in a for this x, is the integral from c to a of f of t dt. So that's from c to a. That's this yellow area right here. And we are subtracting these two things. So think about it. If this blue integral is this blue area, and I'm subtracting from it this yellow area, what am I left with? I'm left with the integral, the area from a to b of f of t dt. Now, this might not seem all that important to you in this moment. You might be like, yeah, so what? You just drew a picture. But that is the second piece of the fundamental theorem of calculus. We're going to take out this middle piece and use these. So the second part of our fundamental theorem says the integral, I'll put it in green again, the integral from a to b of some function with respect to x, or it could be f of t dt, it actually doesn't really matter, is equal to capital F of b minus capital F of a, and we're still back up to this thing, f prime of x is equal to the function in here, or we can say where f is known as an antiderivative of our function f. And to say it's an antiderivative, that means the derivative of uppercase f is lowercase f, or the integral of this thing. Oh gosh. I'm sorry, I totally lost my spot because of that bell. But I think the thing I want to mention really quick is to remind us that this gives us the signed area under the curve, which if it's above the x-axis, it's positive, below the x-axis is negative. I am going to skip ahead to a couple things in 6.6. I'm going to give you some properties of integrals, and then we'll do a bunch of examples in class. So I realize we're totally skipping ahead, but I think it's okay because we're just kind of talking about the content, and we will do examples together, which will help. So let's look at an integral. Let's say we've got some function. Here's a, here's b, and here's c. And we're going to come back to these ideas in a moment. But the first thing to say is that if f and g are integrable functions on an interval from a to b, so both f of x and g of x are both functions that can be integrated, and k is a constant, then the function k times f and f plus g are also able to take an integral of on an interval from a to b. First property is the constant multiple property, which says if I have the integral from a to b of some constant times that function with respect to x, I can pull this constant out. It's equal to k times the integral from a to b of f of x dx. This is actually a property we've seen so many times before, especially with derivatives, right? The derivative of 4x squared is equal to, oh my goodness, someone is moving desks. The integral of 4x squared is equal, not the integral, oh my goodness. The derivative of 4x squared is equal to the derivative of x squared, 2x, times 4. Second property is the additive property for integrals, and this one I think will make sense when we look at our picture. It says, actually this is not the one I was thinking of, but that's okay. The integral from a to b of some function f of x plus or minus some function g of x, all with respect to x. We can break that up into the integral from a to b of f of x with respect to x plus or minus the integral from a to b of g of x with respect to x. Sorry, that one's a little long. We're going to squeeze that in here. Oh, it's so beautiful. Now is the one, I'm sorry, that I wanted to show the picture for, and it's the additive interval property for integrals. That's a lot of words. That says if I have the integral from a to b of some function with respect to x, so that's like this drawing right here, this area is equal to the integral from, let's go with green, a to c of this function with respect to x plus the integral from c to d. Excuse me, c to b of our function. I think that one helps to see the picture, right? It makes sense. If I'm finding all of this area from a to b, well, I could break it up from a to c and then from c to b. And then last but not least, two special integrals. The first is if I take the integral from a to a of some function. Let's think about this. That's the area under the curve from a to a. Well, notice that there's no width here, so it's some height times 0 width. What would that area be? It would be 0. And then the second one says if I am looking at the integral from a to b of some function with respect to x, and I change those bounds, the integral from b to a, so I basically go the opposite direction, this is the opposite area, negative area. That one maybe isn't quite as intuitive, but it is a property that we are going to see again and again in these sections. So we will do all of the examples in class next week. If you are feeling a little shaky on these ideas, don't stress yet, right? We haven't done the examples, and we will get there together. Have a great rest of your day.